So 3.3 is called, or this section is optimization. And what we're going to be looking at is optimizing a function. And what this is finding the minimum or maximum values. Now we've done, oops, sorry about that. We've done relative minimum and relative maximum, and we'll still be applying that, but we're going to go one step further. Now, in real life, in businesses where they look at optimization, an example would be such as looking to or maximizing your profits. So a business is going to look at cost, revenue, profits. They want to maximize those profits, get the most out of their business. It could also be minimizing the time required to complete a task. Obviously, they want to get the most out of their employees. So how can we complete this task but use the least amount of time? Now, we have done relative minimum and maximum, and we know that in order to find relative minimum and maximum, we use the first derivative test. And the first derivative test allowed us to find our critical numbers or our critical values. So we would have a graph that would hit a particular value, increase, and then decrease. We also had situations where it would decrease and then increase. Now, when we were dealing with the first derivative test and relative minimum and maximums, then we knew that this was a relative maximum at the point x equals c. And we know, or would know, that this is a relative minimum at the point x equals c. So we've done that. What we're going to add to today is what is called absolute extrema. Need a T in there. Now, here's what's different. Instead of relative minimum and maximum, it is absolute extrema. Now, this is still a minimum and a maximum. So because of extrema, we're still talking about maximum and minimum. But now because it's absolute, then we want the very highest number or largest and the very smallest, the greatest number, the least number, which gives us our absolute. Now I'm going to go over to Desmos and show you this function, 2x to the fourth plus x cubed minus 3x squared plus 4. Now, here I have this function already entered, and we can see this graph right here. And if we were talking about relative minimum and maximums, here would be a relative minimum, relative minimum, relative maximum. Now, if we were talking about absolute, well, the very absolute least would be right here. So this relative minimum would also be your absolute minimum, but the absolute maximum, it doesn't necessarily have to be here. It's like, of the whole graph, what is the largest output? And this would go on and on and on and on, and it would be infinity, right? So in order to find absolute extrema, you must have a restriction on your domain called endpoints. So now when I look at this graph, what is my highest part of my graph? Well, it would be here and also here at this endpoint. The minimum would be right here, which happens to be an endpoint. So that is one place where absolute is different, because now we are considering the endpoints as well. So the characteristics that go with absolute extrema, the first thing is it has to be a closed interval. So when we first looked at this function, we didn't have, we found what was a minimum, but the maximum just kept going and going and going until we put a restriction on the domain. So we then had a closed interval. So I had a starting point and an ending point to my graph. So it has to be a closed interval. Your absolute extrema will occur at a critical number or numbers and the endpoints. So we have to consider every critical number, every endpoint, and to find the absolute extrema, once we have these, we will evaluate at the original function f of x at every critical number and endpoint. Then we'll look at what is the greatest output. Then that'll be your absolute maximum, and the least output will be your absolute minimum. So we are going to see how this works in an actual problem. So we're going to do an example. So if we're given the function 1.2x squared minus 4.7x plus 10.8, and the domain is 0 and 5, any number in between. All right, so X represents the age of a copier. So of course, zero would represent brand new copier. 5 would represent the copier is 5 years old. Output is the number of repairs required annually. All right, so we have a closed interval. So what we're going to do is we're going to find absolute extrema, which means we need to find all the critical values or critical numbers and also consider endpoints. Well, obviously we already have our endpoints, but we don't yet have our critical number. And in order to get to our critical number or critical values, we know that we have to apply the first derivative. So we're going to take the first derivative of our original function, which is 2.4x minus 4.7. So we set that equal to 0 and solve for x. which is approximately 1.985. This is my critical number. So when we are looking at to find absolute minimum or maximum, we have to evaluate at every critical number. This particular problem just has one critical number, and we have to also evaluate at our endpoints. So we are going to evaluate the original function at the endpoint 0, the critical number 1.985, and this would be approximately 2 years, and then the other endpoint 5. So we know input is age, output is number of repairs. So 0 in this original function, that's 0, so it'd be output of 10.8. This number, plugging it into the original function, gives you an output of 6.19877. Input of 5 gives you an output of 17.3. So the copier is 5 years old. It requires 17.3 repairs for that year, which could get costly for a business. All right, so when we look at this output to find absolute extrema, we want to find the smallest output, which would be here. So this is my absolute minimum. And then we want to find the largest, which would be here, which would be your absolute maximum. Okay. All right. Let's go ahead and answer some questions, and then we'll take a look at this on, well, no, I'm going to go to the graph now. So y equals 1.2x squared minus 4.7x plus 10.8. And then it is from 0 to 5. That's my, so let me make this a little bit smaller. Okay, so right here, and we said our absolute minimum was an input of 1.985 and an output of 6.19877. So here is, now this happens to be a relative minimum as well, but it is also our absolute minimum. And then our absolute maximum was 517.3. And as you can see, very tallest number, the greatest, is your absolute maximum. Types of questions that might be asked. Find the year of the least repairs. Now, repairs is output. Find the year. This is your age. So what was the age of the copier for the least repairs? Least repairs is 6.19877. So the number of years would be 1.985 years. Of course, it could be approximately 2 years. All right. Another question that might be asked. What is the least number of repairs that the copier will require annually. Of course, least repairs, output is repairs, the least, so it would be 6.19877 repairs, or approximately 6 repairs for the year. Now, think of a copier. You have the people that produce and sell the copiers. This information is going to benefit them when they decide what their warranty will be. Do you think they're going to have a warranty at 5 years? That was the maximum number of repairs. They don't want to have to make those repairs without getting paid for them. So this helps them figure out what they want their warranty to be. As far as the business that purchased the copier, they would look at this and go, okay, at what point is it costing me more to pay for repairs yearly than to just get a new copier? So those are some examples for when a function like this and looking at your absolute extrema would help make good, sound financial decisions. We're going to look at another example, just the mathematical part of this. So the function f of x is equal to the cube root of x squared, -1, 8. Now, if you remember, this is interval notation, but basically it means that x is between -1 and 8, and because these are brackets instead of parentheses, it means it can also be equal. So this means the same thing. All right, so if we're asked to find the absolute extrema, again, I need my critical numbers and my endpoints. Now, here's where you need to be careful. Critical numbers means I need to take the derivative of this. Don't yet start taking the derivative until you convert the form of this, because we don't leave it as a radical. So I'm going to rewrite this function as x to the 2/3. Now we can apply our derivative rules, okay? So now we're going to take the first derivative, which would be 2/3 times x. 2/3 minus 3/3, you get -1/3. 2 is in the numerator. 3 is in the denominator. Since this is negative, I'm going to bring it down to the denominator, and then I'm going to rewrite it as a cube root. So these mean the same thing. Now, in this case, we're not going to set it equal to 0. We have a radical. So what value makes the denominator equal to 0? That one's pretty easy, when x is equal to 0. Now, I do want to look, if you recall, if your numerator is 0 and your denominator is a number, then it can be equal to 0, but we don't have any variable in the numerator. So this is my only critical number. So for absolute extrema, then we are going to use the original function, and we're going to consider the inputs and our critical number. Again, we're putting it into the original function. -1 squared is 1. The cube root of 1 is 1. 0 squared is 0. The cube root of 0 is 0. 8 squared is 64. The cube root of 64 is 4, because 4 times 4 times 4 is 64. So then we want to look, my output. Here's my smallest value. That's my absolute minimum. largest value, absolute maximum. All right, now, this section also has us look at a business application. And we've dealt with profit, revenue, and cost previously, but this is going to add some additional things to that and steps. It now has lowercase p of x. This is your price function, which is, this is the price at which consumers will buy X amount of products. So if I buy 5 products, there'll be a given price function, plug it into there, and I'll know what my price is. All right. Now we have done profit equals revenue minus cost, which of course is P of X equals R of X minus C of X. We've already seen this. Now we're going to elaborate on that. Previously, our cost function was given to us, but now we're going to be given information and you have to create the cost function, which is going to be equal to the cost per unit plus any fixed costs. Our revenue function is equal to the unit price times your quantity. Now, your unit price is your price function. Your quantity is how many items that you are buying. Okay, so in essence, your revenue function is P of X times X. Okay. Now, one thing that we know is your quantity is X, P of X is the price, and typically it will look like this, meaning the more that you buy, your price will go down. So if you've ever looked to a fundraiser and sell t-shirts, if you buy 10 t-shirts, they may charge you $15 per t-shirt. But if you buy 50 t-shirts, they'll charge you $8 per shirt. And then if you buy 100 t-shirts, they'll charge you $5 per shirt. So obviously, the higher the quantity, then your price will go down. All right, now let's take a look at an example. We're going to be using all of these to create our, or to find our functions. All right. So your price function is given as 22,000 minus 70x. So this is the price it will cost when you buy X number of the product. So if I buy one product, it's going to be 22,000 minus 70. If I buy 5, so forth. You get the idea. All right. So we're also given that the cost of production is 20,000 plus 8,000 per unit. Okay. All right. So we are going to be asked to find the revenue function, the cost function, as well as the profit function. All right, so I'm going to start with the revenue function. So if we go back, the revenue function is unit price, which is P of X times quantity. So my revenue function is going to be P of X. Sorry, I have an alarm going off. Times quantity, which is X. So of course, we're just going to go ahead and distribute that. So we would get 22,000 X minus 70X squared. So our revenue function is right there. Now we are going to find our cost function, C of X, which is your cost per unit plus fixed costs. Cost is $20,000. That's your fixed unit plus your cost per unit. So this would be 8,000 per unit plus the $20,000 that is fixed. So our cost function is here. Then we are going to get our profit function, which is revenue minus cost. So my profit function is revenue minus cost So of course that's 22,000x minus 70x squared minus 8,000x minus 2,000. So our profit function is like terms 14,000x minus 70x squared minus, and that is 20,000, not 2,000. That would not have been good. All right, so we're going to answer some questions, and here are the functions that we'll be using to answer those questions. What is the company's maximum profit? The company's maximum profit. All right, we need to look at the word maximum, and we need to look at the word profit. All right, so that tells me that I need to find my critical numbers, because that's where we find relative maximum and minimum. And then once I do that, I need to determine if that critical number is a maximum minimum. And how do we do that? We determine if it is concave up or concave down. We can find this at the first derivative. To determine if it is a maximum or minimum, we're going to have to look at the second derivative. And this is profit. So we are going to use our profit function that we created, which was 14,000 x minus 70x squared minus 20,000. So to find the critical number, we're going to take the first derivative, which is 14,000 minus 140x. So of course, we're going to set that equal to 0 to find the critical number. So we get x equals 100. So this is our critical number. Now, we're not done because we do have to determine if it's a minimum or a maximum. So we look at its concavity and we want to know if it's concave up or concave down. And that's just is determine whether the second derivative, if the output is positive or negative. So we're going to find the second derivative. So here's my first derivative, which equals negative 140. And since this is negative, then we know the second derivative is less than 0. So we know we have concave down, which means that we have a max. So because this is negative, we know that this is a maximum. All right, so this is at x equals 100 is where they will maximize their profit, okay? So part B, what is the price to purchase 100 of the product? And so we go back to our given price function and do P of 100, and that was 22,000 minus 70x, which gives us $15,000.